Living things need the Goldilocks conditions in order to survive. The real question is it possible for life to thrive external from Earth? The Goldilocks conditions encompass the circumstances needed for an area of space to be capable of fostering life. Two important factors to look at are the light spectrum and gases in space. Electromagnetic radiation is one of the many ways that energy travels through space. On the surface of the Earth, these types of radiation are not significant health hazards because of the Earth's atmosphere and magnetic field protect us from most of the radiation from space. Radiation becomes a much bigger problem in places outside these protective barriers, like the Moon or Mars. Gamma radiation can penetrate the human body and cause radiation poisoning. Too much ultraviolet can damage the eyes with cataracts and cause skin cancer like melanoma. Natural background radiation comes from cosmic sources like galactic cosmic rays, solar radiation, and from terrestrial sources like rocks and radon. Our protective atmosphere also holds carbon dioxide and other gases that keeps our planet warm. Nitrogen, oxygen, and argon are the main gases of the air we breathe, but this also includes small amounts of water vapor, carbon dioxide, methane, nitrogen dioxide, and sulfur dioxide, a wide variety of gas mixtures.
The planet's atmosphere plays a vital role in whether or not life is obtainable. For a planet's atmosphere to be sustainable for life, it needs to have specific traits. For example, that atmosphere cannot be either too hot or too cold for water to be maintained at a liquid state. In Earth's atmosphere, we have a temperature that is just right for the flow of water across the surface. This allows continental drift, which inevitably helps aid refreshing the Earth's atmosphere. The climate of our planet is an important key, and without an appropriate temperature and atmosphere, life would not be obtainable on Earth.
During vegetation, plants need to be able to constantly grow. If temperatures are too hot or too cold, the plant will result in abnormal growth or no growth at all. Also, the plant will not be able to perform reproduction.
A lot of the odds that are considered in determining the likeliness of extraterrestrial life are uncertain. We do not yet and may never have the technology to venture outside our solar system, and therefore there are several gaps in our knowledge of the universe. However, we can approximate the inner and outer radii of the habitable zone of a main sequence star such as our Sun. Using this equation, where capital M sub v is the absolute magnitude of the star, lowercase m sub v is the apparent magnitude of the star, and d is the distance from Earth to the Sun in parsecs, we can find the absolute magnitude of the star. With the absolute magnitude of the star, we can then calculate the bolometric magnitude of the star using a table for bolometric correction values. In this equation, capital B is the bolometric correction constant specified on the table. After finding the bolometric magnitude of the star, we can then determine the absolute luminosity of the host star by putting it in terms of the absolute luminosity and the bolometric magnitude of the Sun. The left side of the equation represents the absolute luminosity of the star in terms of the absolute luminosity of the Sun. The constant used in comparing luminosities is 2.5. When the absolute luminosity is solved for, these equations can determine the inner radius, r sub I, and the outer radius, r sub O, of the star's habitable zone in astronomical units. 1.1 and 0.53 represent the constants used for stellar flux at the radii of the habitable zone.